Okay, so if we sum up these values, what would we get? If we sum up these values, what should we get? We get 6 plus 10, 16, plus 18 comes out to be 34, plus 15 comes out to be 49, plus 3 comes out to be 52, plus 3.33 comes out to be 55.33. So this is the total profit that we get by applying the greedy knapsack or the fractional knapsack using the greedy approach. Okay, so I hope you have understood this. Now I'll take up another example. Okay, let's see how this is done now. Again, the first thing to do is to find the profit per weight. So let's find the profit per weight for every object. Let's find the profit per weight. Simply take the profit and you divide it by the weight. So you get 2, 28 by 4 is 7, 25 by 5 is 5, 18 by 3 is 6, 9 by 3 is 3. So you get the profit per weight. Now you arrange these objects in non-increasing order of this value. You arrange them in non-increasing order of profit by weight. So if I arrange them in non-increasing order, first you get object 2, then you get object 4, then you get object 3. See, first 7, then 6, then 5. I'm going in decreasing order. Either the values will be decreasing or they'll remain the same. So 7, 6, 5, and then comes this object 5, and then comes object 1. So these are my objects. These are my objects after arranging in non-increasing order of this parameter of profit by weight. Now I'll choose the objects in this order such that the capacity of the knapsack is not exceeded. The capacity of the knapsack given to us is 15, right? And here n is not 7. So consider this typographical error. N is 5 because you have 5 objects. So now what do we do is we choose the objects. So we'll find the maximum profit. Now which object we'll choose first? We'll choose object 2. Object 2 has a profit of 28. So we take this entire instance of object 2. We take the whole instance. So if we take up the whole instance, the capacity of the knapsack, which is 15, will reduce. How much will it reduce by? It will reduce by the weight of object 2. What is the weight of object 2? 4. So the capacity of the knapsack reduces by 4 and it becomes 11. Next, we choose object 4. Object 4 has a profit of 18. So we take a profit of 18 and it has a weight of 3. So the capacity of the knapsack will reduce by 3 and it will become 8. Next, we choose object 3. Now object 3 has a profit of 25. Object 3 has a profit of 25. And along with that, if you notice, it has a weight of 5 units. So this entire instance of object 3 has a weight of 5. So if I add this entire instance in my knapsack, the capacity of the knapsack will reduce by 5, will reduce by its weight, and it will become 8 minus 5, 3. Next, we have object 5. Now object 5 has a profit of 9, and look at this, there is a complete match. See, it has a weight of 3. This entire instance of object 5 has a weight of 3 and the capacity left in my knapsack is also 3. That means I'll use up the knapsack in totality, and I have how many objects in my bag? I have 2, 3, 4, 5. I have 4 objects. So object 1 does not make it in my knapsack. In spite of that, we will get the maximum profit. So if you calculate this sum, what will you get? 28 plus 18 comes out to be 46. 46 plus 25 comes out to be 71. And 71 plus 9 comes out to be 80. So this is our maximum profit. Okay, so I hope you have understood the way you will need to solve problems on fractional knapsack. Next, I'll take you through the algorithm. Let's just walk through the algorithm. Now, if you have gone through the previous video as well as the beginning portion of this video, of the current video, you would probably have understood how to solve problems of fractional knapsack using the greedy approach. Now what I've done is I've written down the algorithm for the entire procedure using which we calculated the maximum profit. So as you can see, the greedy knapsack will take 4 inputs. The first input is the size of the knapsack, which is denoted by the variable m. the number of objects present denoted by the variable n, the profit of every object given to us. That means this will be a list of profit values of the objects, and this will be a list of weight values of the objects. Now what I'll do is I'll simply calculate, like you saw in the examples that we solved. You saw that first thing was to calculate the profit per weight, profit per unit weight. So what we do is for every object, so for I equal to 1 to n, n is the number of objects present. So I'll start from the first object and I'll go up to the nth object, that means the last object, and for each object I'll calculate the profit per weight and I'll store it in a list. Here by list you can implement it as an array. Next step is to sort the objects in non-increasing order of profit per weight. So we'll sort the objects in non-increasing order of profit per weight. That means we'll arrange them in either decreasing order or in the order where two values may be the same. So after arranging the objects in non-increasing order of profit per weight, what we'll do is from the sorted list, we'll start right from the first object. So we'll choose an object and we'll check m greater than 0. This m greater than 0 signifies that the knapsack still has some space in it. And along with that, another criteria has to be satisfied. And that criteria is the weight of the object. Which object? The ith object. See, w suffix I denotes the ith object. So if you have n as 4, that means if you have 4 objects given to you, your loop will run from 1 to 4. So you will check for w1. That means you will check for when I is equal to 1, this will be what? This will be w1. That means that will correspond to the weight of object 1. When I will become 2, this will be w2, the weight corresponding to object 2. So if the weight corresponding to the ith object, if that happens to be less than your knapsack and there is still some space left in your knapsack, that means its size, its capacity is greater than 0, then you enter this body of if. And what do? You subtract, like we saw in every step of the numerical that we solved. We saw that we were decrementing the capacity of the knapsack by the weight of the item given to us. So that's why you have this step. So you decrement the capacity of the knapsack by the weight of the object currently being processed. And along with that, you add the profit. You add the profit of the object. You add the profit of the current object being processed, the ith object. And if this condition does not happen to be true, when will the condition be violated? This condition will be violated when the capacity of the knapsack will be 0, right? When the capacity of the knapsack becomes 0, that means there is no more space left in your knapsack, then this condition will be violated. Or it may happen that the weight of the current object being processed is no longer lesser than the capacity of the knapsack. That means it may happen that the current object that you are processing, it has a weight which is greater than the current capacity of the knapsack. So if either of these conditions is violated, you will simply come to the else part where it is written that you have to break out of the loop. So you will come out of the loop, and here what will happen is you have to deal with the fractional portion. That means it can happen that this condition is satisfied. Because of this, this condition is not satisfied. Sorry about that. If this condition is not satisfied, then also you will come to the else part. And in that case, what does it mean? It means that this condition has been satisfied. So if this condition is satisfied, that means there is still space left in your knapsack. M denotes the size of the knapsack, and if M happens to be greater than 0, that means there is still space left in your knapsack. And in spite of that, since the current object which you are processing, its weight, its total weight, the weight of the entire instance is greater than the current capacity of knapsack, you had to come out of the loop. That doesn't mean that you will lead or you will let go of the remaining part of the knapsack. The remaining part of the knapsack has to be filled up with the fractional portion of the current object. So that's why what you do is you apply this. So you take the fractional part. If you remember from the example that we did, I'll show you the example so that you can recollect. So if you remember this example, see here what happened was we were choosing object 5, we took object 5 in its entirety, object 1 in its entirety, entire instance of 6, entire instance of 3, entire instance of 7. But when it came to object 2, we saw that the weight of object 2 is 3. the entire instance of object 2 weighs 3, but the capacity of the knapsack that was present when object 2 was being processed was 2, but its weight is 3. So we cannot take this entire instance and put it in a knapsack. We'll have to only take a portion of it. How much portion? 2 parts of it. Out of this entire part, we have to take 2 parts of it. That's why we applied the unitary method and came up with this value. So it was 5 by 3 into 2. Now if you just map this to a formula, what will you get? What is this 5? This 5 is the profit. This 5 is the profit of which object? This 5 is the profit of our current object. And which is our current object? The current object is 2. So you take the profit and you divide it. You divide it by 3. What is 3? 3 is the weight. 3 is the weight of object 2. So I write W2 and you multiply it. What do you multiply it with? You multiply it with the current capacity of the knapsack. What is the current capacity of the knapsack? The current capacity of the knapsack is M. So if you apply this formula, like I showed you using the unitary method, you can generalize it to this formula. Now if you compare this formula with this part. Look at this. You compare this part with this. See, it comes out to be the same. So you're taking the profit of the current object. Here I is what? You're dealing with object 2. That means your I is 2. So here P2. So in place of I you place 2. So P2 into M, see, into M divided by Wi. That means W2. So I means the current object, the index of the current object being processed. So P2 into M by W2. So that's why this unitary method has been summed up in this formula, in the algorithm. So I hope you have understood this. So if a portion of the knapsack is left, you fill it up with a fraction of the object. And if you observe, let's try to walk you through the time complexity and space complexity. The space complexity, I guess you have understood, since we are not using any auxiliary memory, we are not using any additional lists or arrays. The space complexity is order of 1. But what about the time complexity? Let's see what happens. Let's try to find the time complexity. See, if you have to find the time complexity, you have to go through each key operation. So this is a key operation. So you're going through n objects. So this part will take up order of n time. Now sorting is a major operation. And which is the best sorting algorithm known to you? The best sorting algorithm known to us is merge sort. And merge sort has a worst case complexity of order of n log n. Order of n log n. So this is another key operation that we do. And what about this part? This entire for loop? This entire for loop can go up to order of n, because you have to do it for n number of objects. In worst case, you have to go up to n number of objects. And this part is going to be performed only once. This checking is performed only once. So this is order of 1. Now, so what does the total time complexity come out to be? The total time complexity comes out to be order of n plus order of n log n plus order of n plus order of 1. Now out of these 4 terms, which is the leading term? The leading term is order of n log n. That's why we say that the greedy knapsack algorithm has a time complexity of order of n log n. So this is one approach. Now another approach could be, in place of sorting the objects, you can try and build a heap. So let's see what would that approach be like. So a heap implementation can be adopted in place of sorting. So what do we do? In that case, instead of applying sorting, we go for a max heap. Now in max heap, we need to do the following. See, you're trying to arrange the elements in non-increasing order. That means the elements will be arranged from a higher value to a lower value. So you're talking about decreasing order or the elements remaining the same. In such cases, you would always go for a max heap, because you would have to build a tree in that way. So to build a max heap, you need a time of order of n. We know this, right? We have seen this in our video on heap sort, that to build a max heap, we need a time of order of n. And what do we have to do? We have to delete the maximum node n times. We have to delete the maximum node n times. And for each deletion, what do we have to do? For each deletion, we have to cover at most the height of the tree. And what is the height of a heap? Since heap is a complete binary tree and the height of a complete binary tree is order of log n, we have to at most travel or at most make log n comparisons. Now for n nodes, if we make log n comparisons total number of comparisons required is n into log n. And now if you take these two key operations and if you sum it up, you find that n log n is the leading term. That is why the time complexity in this case, instead of sorting, if we build a heap, in that case as well, the time complexity will be order of n log n. So as such, we can see that there is no advantage compared to sorting if we apply the heap approach. So this was all about greedy knapsack. I hope this video turns out to be useful for you. If you have any questions, please feel free to leave them in the comment section below. I'll see you in the next one.